Yeah. Yeah. Over.
Yeah, but if I break it, it's in.
Right.
Breaks it. Place the wheel.
Stop. I was, yeah, no, it was so funny. It's like, yeah, it's so she's called. I really like when she's called. No, it's like the best part. It's like my papa. It's like maybe, yeah, we'll get it.
Once left.
No, it starts to like, yeah.
Yeah.
Also makes us so really much. Yeah. I have been since like. Yeah, I know. Yeah. Wait, really? Oh, yeah. Like, we just like. Yeah, I was like, yeah, I was like, but like, we know those things. So it's like a fun, so like, you just like look and see everything. So I was hoping like videoed it or something. It was so. I know, yeah, it was awesome. Like all these things, like watching. Yeah, like we were just it was hard to like God, it's not small, yeah.
Was you.
Yeah. Yes. No, that's with this week and next week and that's.
Maybe when you don't decide.
Yeah. Yeah.
All right, welcome back. Hope you guys had a nice break. This semester, we're going to be talking about antiderivatives, which is working backwards from derivatives. Basically, the big picture is that we're undoing all the process that we learned with first semester. So very much like, a lot of times when we learn math, we always learn to do something and we learn to undo it, right? So we learn addition first, then we learn subtraction. We learn multiplication, then we learn division. So the connection there is, we're learning derivatives, and now we're learning to do antiderivatives, working our way back to where we came from. So a lot of the rules that we learned first semester, we can, if we think about, how do we get back to where I came from, then in that sense, are the rules that we're going to learn, integral rules are just going backwards to from the derivative back to the original function. So there's some slight adjustments, but for the most part, that hopefully that will kind of keep it where, it doesn't feel like completely these new rules that we're learning. We're just learning to go backwards from the rules that we learned initially. Another big connection that I want to make, and I'll make this probably a little bit later over the course of as we move into power rule and integrals. And right now, I just have to I just want you to watch this demonstration here. So if we think about slope, slope has a divisional quality to it, right? I mean, we see subtraction, but the big operation there is division, right? Change in y over the change in x, right? Rise over run. That gives us slope. That gives us that the rate of change at a point. And calculus, we're able to take that slope information and pinpoint it to a specific point and not just between two endpoints. So imagine if we wanted to undo this process, right? How do we undo division? What's the opposite operation of division? Multiplication, right? So if I want to multiply these two together, it'll be x sub 2 minus x sub 1 times y sub 2 minus y sub 1. Okay. Now, that may not look like anything to you, but if we just think about what that looks like, okay, x sub 2 minus x sub 1, let's say this is x sub 1, this is x sub 2, and then y sub 2 minus y sub 1, y sub 2 minus y sub 1. So if I have this times this, what is that going to get us? If I multiply this value with this value, geometrically, that gets us what? Area of a rectangle, right? So that's why with derivatives, we talk about slope, but with antiderivatives, we talk about area. Because if we undo this process, we're going to essentially get length times width, which is area. So a lot of things that we're going to do before we talk about integrals is we're going to talk about representing area of a region. And the reason that we talk about area so much is because that is the opposite operation to allow us to get back to the original function. If we took the derivative to get to from f to f prime, the way we undo that derivative is through multiplication, through undoing that divisional process, and that visually is going to look like area. Okay. So we're not going to really get much into area today. We're going to talk about the tools that we need. So we're going to talk about sigma notation today. And then tomorrow we'll talk about how we can use rectangles to approximate a region. The reason we say approximation is because we're going to be looking at curved regions. So rectangles can only do so much in terms of representing that area. It's not going to be exact, but because rectangles are the easiest shapes for us to build areas, we're going to start with rectangles, and then eventually we'll bring in the calculus, and then we'll bring in the more efficient way of getting to that area formula, which is using power rule. So we will start reviewing next week, and hope to have a quiz over these three sections on Thursday. Okay, so let's start with this. So if you remember back, this may be a couple of years since you've done anything with sigma notation, but all this means is it's just a representation of adding a bunch of numbers together. Right? We're just adding a bunch of numbers together, but it's represented in a kind of like in a condensed expression. Okay, so when you see that sigma notation, that just means, okay, we're going to be adding a bunch of values together. So here is the way this works. We first have an index. Index represents the variable that we're going to be starting the value with. So our index value 2 is the lower bound. This indicates the first value that we're going to plug into our formula. And this is the upper bound. This is the last value that we plug into the formula. This a sub I is going to be our formula rule or our argument expression. So the way it works is once you plug in you're always going to be told what lower bound to plug in into your expression. Then the next expression is always going to be 1 above it. So if we start at 3, then the next number you plug in is 4. And we just always increment by 1 until we reach the upper bound. This is the last value that we plug in. Sometimes students misrepresent this number thinking, oh, this must mean there are 5 terms that we add together. Not necessarily. It's only 5 terms if we start at 1. But if we start at 2 or we start at a different number, then this is not going to represent the total number of terms. So don't think of this as total number of terms. This is the last variable value or last value to plug into the variable. So if I want to represent the value of this sigma notation, then we plug 2 in first, and we do a sub 2. Then we increment to 3, because that's the next number above 2. Then we do a sub 3 plus a sub 4 plus a sub 5, and we stop when we reach that final upper bound value. Okay, so in this case, there's only 4 terms that we add together. Okay. Oh, and also I call this the rule of sequence as well. So using what I just described, try example 1. Your lower bound is 2, your upper bound is 4, and your rule of sequence is I squared plus 1. So see if you can plug in the values and add the terms together and see if we match. Okay, so 2 is the first value that we plug in for I. So 2 squared plus 1, that represents a sub 2. And then plus, we always move to the next number above it. So next number is 3. 3 squared plus 1 is my a sub 3. And then my a sub 4 is 4 squared plus 1. And then I stop there, right? Because we've plugged in the final, the largest value, our upper bound value. And now we just add all these numbers up. 4 plus 1 plus 9 plus 1 plus 16 plus 1, 32. Now, this is not difficult, but you can imagine how tedious this can be, especially if we have more terms to add, right? Imagine going from 2 to 24, right? That would just, we're just doing a bunch of calculations. There's not a lot of interesting element to that. It's just number crunching. So we have these formulas that allow us to have a little bit of a shortcut for these specific scenarios that we're going to see leading up to. So we're just basically building the tools that we need to eventually add up a lot of terms together. So these formulas, they all start at I equals 1. And the first rule of sequence is 1. So imagine if the rule of sequence is 1. So basically it's just 1 plus 1 plus 1 plus 1 all the way to the last term. And because we're adding a bunch of 1s together, the sum of this is just going to be whatever that upper bound is. So if the upper bound is 10, then we're just adding 1 10 times. So my sum is just going to be that n if my rule of sequence is 1. This makes sense, right? The second rule is, imagine if my rule of sequence is I. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way to my upper bound, which could be 20, could be 100, could be 200. rather than adding all those numbers up, we can just go through the formula, which just says take the upper bound, multiply the upper bound by the upper bound plus 1, and divide by 2. So if it was from 1 to 10, and if I'm adding 1 plus 2 plus 3 plus 4 all the way to plus 10, I should do 10 times 11 divided by 2, and that will give me my sum. The third rule is if it was 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, that would be taking the upper bound, a little bit more complicated, n times n plus 1 times 2n plus 1 all over 6. And the fourth rule is if it was 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way to n cubed, if I were to add up all those terms together, the shortcut is take the upper bound, n squared times n plus 1 squared divided by 4. And on the quiz, I will give you these formulas, so you want to memorize them. Okay, just have to know how to use it. And then the fifth one is more of just rearranging to help things be a little bit easier to look at. So if I have any coefficient that is attached to my rule of sequence, I can always push it out in front so that it doesn't kind of get in the way. I can kind of just kind of push it to the front and then let it attach to at the end. So it's just a rearranging to make our rule of sequence a little bit cleaner, not having to look at a coefficient until the end. Okay, let's look at example 2. So example 2, we have summation of a rule of sequence from 1 to 8. So we could do this by hand, plug 1 in, 3 plus 2, then plug 2 in, 3 times 2 squared plus 2, then 3, then 4, then all the way up to 8. But we're going to practice using these rules so we can eventually be more, so that we can be able to apply these rules later on when we really do need it. Now, these are actually two separate rules here. So the 3i squared is going to be, we can think of it as separate from that plus 2. So I'm going to think of this as the same thing as if I were to do this. From 1 to 8 of 3i squared plus the sum from 1 to 8 of a rule sequence of 2. And I'm going to take advantage of this property so that I can match these with one of these 3 rules that I want to use. So that 3 I can push out in front. And I can also push this 2 out in front, because if I push the 2 out in front, what's left? What's left here? 2 times what gives me 2? 1. Yeah, so I can use that summation 1, and that matches with this rule that I want to match, that I want to apply. So now that the coefficients are out in front, I can kind of box off these and apply the rules there, and then I can apply the rules there, and then I can just multiply by 3 and 2 once I get that sum figured out. So I'm going to take advantage of this rule, I squared here. So rather than having to add up 1 squared plus 2 squared plus 3 squared all the way to 8 squared, we're just going to apply this rule here. What n value can we use? 8, yep, always the upper bound. So it's 8 times 9 plus 17, or times 17 divided by 6. And I say 17 because 2 times 8 is 16. 16 plus 1 is 17. I can multiply all of that by 3. Right, this 3 is still being multiplied in front. Right? And you get to use your calculator. Okay, but for now, you can kind of just follow along, and you know it's just a bunch of plugging into the calculator. Second one, summation from 1 to 8. this matches the first rule. It's just going to be my upper bound, which is 8. So it's just 2 times 8. Any questions on how I apply the rule or got the problem to match the rule that I want to use? Okay, so all this is just a bunch of calculation in the calculator. So I get 612 plus 16, which is 628. Any questions with 2? So number 3, I'm going to show the first step, and then from there, see if you can use example 2 to help you separate and get it to the point where you can apply these summation rules. So I plus 2 squared is not quite ready for us to apply the rules. So what if we FOIL or expanded this out first? I plus 2 times I plus 2, which is I squared. 2i plus 2i, I'm going to merge the like terms together, make it 4i plus 4. So now treat this like how you did with example 2. Go ahead and split this up into 3 separate summations. Pull the coefficients out in front. Get each of the summations to match one of the 3 rules that you see above. And then replace the ends with the upper bound value. And let's see if we can match it up to get the same sum. If you just want to get to this stage, and then I can show you the sum if you don't have your calculator. But if you can get to this stage, then that indicates you know what how to plug in the calculator, or what numbers to plug into the calculator. So we have summation I squared, summation 4i plus summation 4. Now with the 4i and 4, we can push the 4 out in front, and we get summation I, summation 1. And now we have these clean rules that we can apply from our summation formulas above. So summation I squared is n times n plus 1 times 2n plus 1 all over 6. Summation I is n times n plus 1 over 2. And summation 1 is just n. And all my n values are just going to be replaced with what? 10, yeah. Any questions with 3? Okay, this last one looks a little bit more complicated. But instead of I, they're using K. And then the N is going to be some unknown upper bound. So we'll just treat N like a number, treat it like if it was 10 or 5 or 6. But in the end, we're not going to be able to get away from N. Our answer is going to have N's in it. And then for we're just going to treat K like we do I's. So I'm just going to distribute that 1 over N through, just so I can kind of get this into 2 separate terms here. Just distributing through, and I'm separating into 2 separate sums. And I'm going to pull the 1 over N out in front because there's just going to be some unknown constants. Even though my index is a different variable, I can still apply the same summation rules as above. We can treat this like summation I squared, and we can treat this like summation 1. It's just that now we're not able to replace n's with anything except n's. So summation k squared will just get replaced with n times n plus 1 times 2n plus 1 all over 6. Summation 1 will be replaced with n. And all we can do is represent our answer in terms of n. We're not going to be able to have a numeric value at the end, since our upper bound is not a numeric value. So we can only go as far as what the upper bound restricts us to. So summation I squared or summation k squared is just n times n plus 1 times 2n plus 1 all over 6. And summation 1 is just n. And we do a little bit of cleanup here. These are 2 separate fractions. I can cancel out the n's from one of them. I guess we go a little further, but this is fine. We have everything in terms of n. That's as far as we can go. Now, the point of everything that we're doing today is just we're just kind of building the tools that we need for what we're going to use on Thursday. So right now, it does feel like, wait, where is this leading to? Like, we're not, I thought we wanted to talk about antiderivatives. I thought we wanted to talk about area using rectangles. So we will get there, but we have to kind of learn the tools before Thursday. So next page. So we're going to do a little bit of review in terms of limits as n approaches infinity. Think back about finding horizontal asymptotes, right? And the way we did that was we compared degrees between numerator and denominator. A quick example of this would be if it was like limit as n approaches infinity of let's say 3n squared over 4n squared minus n plus 1. Or imagine if this was x, right? We know that infinity has a different set of rules. We don't plug anything in. We simply look at the degrees. If the degrees match, then it's simply the ratio of the coefficients away. Any of the lower degrees we don't care about. It's just going to drop off. In this case, this example would just be 3/4, right? Because the degrees match and we just compare degrees. So example 5, same process here. If this was the rule of sequence, or this was the function, and if we were asked to find the limit as n approaches infinity, let's just clean everything up here, get it all under one fraction, and see what the degrees are. If the degrees are the same, we can just simply focus on the ratio of the coefficients. So this one, I can make the numerator n squared plus n. My denominator is just 2n squared. And we're approaching infinity. Degrees match. So what's my limit going to be? Just 1/2. Yeah. So coefficient, right? There's a 1 in front of the n squared. There's 2 in front of this n squared. So 1/2. So let's see if we can put it all together from what we did in the first page and this example. Let's see how far we can get. Okay, so here's example 6. Find the limit as n approaches infinity from 1 to n of 2i over n times 2 over n. Let's not worry about the n approaching infinity. Let's just clean up that summation, identify a rule that we can use so that we can get everything in terms of n. The goal is to get everything in terms of n first so that we can compare degrees and eventually find the limit. But first things first, I'm going to try to clean up this expression here. Now, I want to move things in a way where I can apply one of the summation rules. And there's only 3 summation rules, right? There's summation 1, summation I, and summation I squared. So in this case, what's going to be the best fit if we want to match with the summation rule? Summation what? Or what can I move so that I can get a summation rule to clearly show up? What can we pull out in front? So do you guys see it here? Between these 3 rules, what do you think would be the best fits for this problem? Summation 1, summation I squared, or summation I cubed? Summation I, right? So if I want to do summation I, what can I push out in front so I can get that I by itself? Yeah, so that's the first step here. We just want to get that coefficient out of the way because we know those aren't going to change. We're just going to change or impact the parts that's affected by the rule. Okay, so this piece gets replaced. The rule for summation I is n times n plus 1 divided by 2. And now we can involve the limit, clean this up, and compare degrees. I'm just distributing that 4n through so I can clearly see the degrees comparison between numerator and denominator. What's going to be the limit of this expression? Just 2, yep. Degrees match. I don't care about the lower degrees, just the highest degree. And then the coefficients is just 4/2, which is 2. Any questions with 6? Now 7 is just a more complicated version of 6. There's just more things to clean up, but ultimately we're trying to get the summation formulas to be applied. We want to eventually convert all the i's to be in terms of n, and then we can compare degrees and find what the limit is since we're approaching infinity. So first things first, I'm going to make sure that I take the time to FOIL. I can't just distribute that 2 through, right? I want to write that 1 plus 2i over n twice, FOIL that out, then I'll distribute the 2 over n through. Okay, let's try those first few steps. We're just trying to clean all this up so that all the parentheses can go away and we can get all these to be nicely separated. I'm just pushing that 2 over n out in front and taking the time to FOIL, and then I'll distribute that 2 over n through at the end. Bunch of algebraic steps at the beginning. So distribute that 2 over n through. And because we have 3 terms, let's think about splitting them up into 3 separate summations. So from here, see if you're able to create a scenario where you can clearly see a summation 1. This one, let's get this to be a summation I. And this third one, let's get this to be a summation I squared. And then any of the leftover coefficients, let's push them out in front because we know that those will not get impacted by the rule. Okay. Any questions up to this point here? So now hopefully it's more clear as to what needs to be done, right? Now go to your summation rules, replace this with n, replace this with n times n plus 1 over 2, replace this with n times n plus 1 times 2n plus 1 all over 6. And then within each term, see if you can clean up each fraction to the point where you can compare degrees and pull out the fraction that's going to come out of each of those limits. So ultimately, you're just going to apply the limit process 3 times. Compare degrees for this first set of terms, compare degrees for this set of terms, and then compare degrees for this set of terms. Now, we do want to do a little bit of cleanup, so. Now, this last set feels complicated. So I want to talk a little bit about a shortcut in terms of how can we get to the limit without having to FOIL everything out. So, but want to have you guys get to this point first. So 2n over n, degrees match, that's just 2 over 1, that's just 2. 8n squared plus 8n divided by 2n squared, degrees match. Highest degree is 2, my coefficient is just 8 over 2. I can drop the 8n, right? Lower degree is not going to matter. So 8 over 2 is 4. Now this piece feels a little bit more tedious, right? Having to FOIL all this out. Eventually it gives you 16n cubed plus 24n squared plus 8n over 6n cubed. We don't care about the n squared and n, just the highest degrees, so 16 over 6. So 2 plus 4 plus 8/3 is 26 over 3. But I want to talk about a shortcut where you don't have to FOIL all this out in order to get to that result. So here's a way that you can do it without having to FOIL all this out. Now, we only care about the highest degree, right? We know that the lower degree will just drop out. It will not have an impact because it's not increasing at a fast enough rate. So we can do that by just focusing on the first of each term, because we know the rest will produce a lower degree that's not going to impact our limit. So what's 8n times n times 2n? First of each set, what does that give me? Yeah, 16n cubed plus a bunch of lower degree terms. And if I know that I've gathered the highest degree with the coefficient associated with it, I can ignore the rest of it and just focus on that. But if you feel more comfortable pulling everything out, that's fine. But just want to offer a shortcut where if we're only targeting the highest degree, from each set, we just pull the highest degree term and let that guide our process. We don't have to find the rest of these terms because they're just going to be lower and not as impactful. Okay, I have all your homework pages in the packet, so I want to kind of show you where that is. It says, we're starting off with 4.2 first, and then we're going to 4.1. So near the back of your packet, I have 4.2 first. So I think I have it on page, if you can just turn to page 47, so you can see it in front of you. We'll spend a few days on 4.2, and then after 4.2, then I put 4.1 because we're doing approximation first before we move into the calculus. So you're going to be pulling your problems from page 263, which in your packet is page 47. Okay, so your homework tonight is problems 1 through 19, odds, page 263 to 264. Okay. I'll send out reminders this afternoon, as well as the link to this current unit. And from there, you can also find the link to the key where I work out each of the problems. Okay. All right, come get your phones.